So one thing as we're working through forces that we have to be able to do is we have to be able to draw free body diagrams, which is just showing pictures which indicate the forces that are acting on objects, as well as we need to be able to find what's called the net force, which is just the sum of forces. Forces are vectors, so we would add them head to tail, and we're going to mathematically show what the net force is or what the total force is acting on an object, because this is what's actually going to cause the resulting motion. Whether something is going to be stationary or accelerating, it's the net force which is going to cause that, not the individual forces. So when I'm showing the net force, I'm just going to do two quick examples of what this would look like. In terms of the net force, we're always going to break things up into X and Y components. We could find the total net force from those two components. In this case, the sum of my forces in the Y direction, because I have no forces in the X direction, is going to be my normal force minus my force of gravity. And we'll learn that I'm going to cause that to equal mass times acceleration in the Y direction. And this is how I would set up that problem. In this scenario, I have forces both in the X direction and the Y direction. So I'm going to break the forces into just which ones are acting vertically, which ones are acting horizontally. The first thing I'm going to do is break apart this force here, which is a pull force, into an X and Y component, so that then I can do the sum of the forces in either direction, instead of trying to deal this as a force acting in two different directions. So as I'm doing this, this is just a fancy way to write F net in the X direction. This sigma symbol here just stands for the summation, or adding up all the forces in the X direction, adding up all the forces in the Y direction. The forces in the X direction, if that's going to be my positive, are going to be the F in the X component of my pull force, subtracted from my frictional force, and that's going to equal my mass times my acceleration in the X direction. Same thing in the Y direction. I'm going to have a normal force plus my Y component minus my force of gravity, and that's going to equal my mass times acceleration in the Y direction. If I were to know this angle here, theta, what I could do is I could determine X and Y components by saying F of X is F pull times the cosine of theta, and my Y component is going to be F pull times the sine of theta, right? SOHCAHTOA, this is my adjacent side, this is my opposite side, and this is my hypotenuse for that right triangle. So that's how I'm going to set up net force equations. And we need to become familiar with this and be able to work through any problem of determining what are the components of the forces in the X and Y direction and how would those add up, right? We're adding the ones that are positive, we're subtracting the ones that are negative because that's an addition of a negative value. This is going to lead us into Newton's first law. Newton's first law you typically hear as an object in motion stays in motion, or an object at rest stays at rest unless acted upon by an outside force. While this is true, I don't think it really describes what we need to understand mathematically and conceptually as to what's actually happening. So I like to write Newton's first law as this. Simply stated, if the net force is zero, then the acceleration is zero. That means an object can be doing one of two things. It can be at rest, or it can maintain a constant velocity, because acceleration is when our velocity is changing. If acceleration is zero, something moving with a constant velocity is something with zero acceleration. And at rest is also it really is a constant velocity, it's just a velocity of zero. So as long as my velocity is remaining constant, that is what Newton's first law says. If that's true, then the net force must be zero. Here's an example. If we have an object that is just sitting there, it's at rest, it is a book sitting on a table, right? We know that the acceleration in the Y direction is zero. And from that, this entire side of my equation equals zero. And what that can tell me then is that my gravitational force equals my normal force in this circumstance. Okay? That's based on Newton's first law. If it's at rest, the acceleration must be zero. All right, well, let's look over here. Let's say we have this object and it's being pulled with a velocity to the right, and that's a constant velocity, right? So we're pulling a wagon, right? We're applying a flow force. There's a frictional force resisting us, but we're still able to pull it, okay? As long as we know that it's a constant velocity, right, and we're moving in the x direction, we can say that my acceleration in the x direction is 0. That again is going to make this entire side of my equation 0, which that again is then going to tell me that the F of the x is equal to my frictional force. Or another way to say that is that the F pull times the cosine of theta equals my frictional force as well. Okay? Now what you'll see with this is if we're talking about something that's being pulled to the right, it won't implicitly say it, but what it implies is if it's just moving to the right, it's not accelerating up or down either. So that could be at rest in the y direction. So what that's going to tell me as well is that my acceleration in the y direction is also 0. It's not accelerating upwards or downwards. So that again here, my entire right side of my equation is 0. And then I could write that the normal force plus the pull force sine theta equals my gravitational force. So I just plugged in, obviously here for my force of y. Right? And so that's how now we can start to determine what different forces are based upon the accelerations being 0 and that meeting Newton's first law requirement, that if the net force is 0, my acceleration is going to be 0. So we can use this both ways. If we understand that acceleration is 0, then we can say the net force is 0. Or if we know the net force is 0, then we can say an object is either going to be at rest or maintaining a constant velocity. And that's how we work through them in setting up problems dealing with Newton's first law.